Welcome to Talk Tensors. Are you ready to unpack a massive paradigm shift in how we think about artificial intelligence?
Because today we are doing a deep dive into a major breakthrough in how AI models learn to reason implicitly, rather than just parrot back memorized text.
Yeah, if you've been following the viral discussions across social media, Hacker News, and X right now, you know exactly what we're talking about. Everyone is buzzing about how massive foundational models, we're talking the giants like GPT-4 and Gemini, how they completely struggle with seemingly simple leaps of logic if they aren't allowed to think out loud using chain of thought prompting.
It's arguably the defining bottleneck of current AI architecture. I mean, we have these incredible systems that can generate beautiful poetry, pass the bar exam, write highly functional code. But when you ask them to connect two simple facts that are already stored in their own internal weights,
right,
and you ask them to do it without explicitly writing out the intermediate steps, they stumble, they hallucinate wildly, or they just throw their hands up and guess.
Which is incredibly frustrating to watch. And that brings us to the core thesis of today's deep dive. Transformers absolutely can become perfect implicit reasoners over their internalized knowledge. But, and this is a massive but, they can only do it through a bizarre, extended training phenomenon known as grokking.
Yeah, and understanding this mechanism changes everything about how we should be training future models.
Yeah.
It really forces the entire industry to rethink the whole scale is all you need mantra.
Definitely.
For the last few years, the assumption has been that if a model can't reason, well, you just haven't fed it enough data yet. But this underlying mechanic we're about to explore proves that intuition completely wrong.
To really get into this, we need to start by defining what we mean by implicit versus explicit reasoning. I think the best way to visualize this for anyone building or interacting with these models is to step away from the usual whiteboard math analogies and think about how we process complex information natively.
That's a great way to frame it.
Like, explicit reasoning is like writing out a proof line by line. In the AI world, that is chain of thought prompting. You literally force the model to output its intermediate tokens.
Exactly.
But implicit reasoning, that's looking at a complex chessboard and instantly knowing the right move without consciously calculating every single variation. You just see the lines of force.
And current state-of-the-art large language models are severely deficient at that kind of implicit, instantly resolved reasoning. The real-world example causing all the stir right now, the one that really highlights this failure, is the Barack and Michelle Obama test.
Oh yeah, the classic relation test.
Right. So a massive language model perfectly knows the atomic fact, Barack's wife is Michelle. If you prompt it for that, it gets it right 100% of the time.
Right, it has that memorized.
It also perfectly knows the separate atomic fact. Michelle was born in 1964. But if you give it a prompt that requires implicitly chaining those two facts together in a single forward pass, like asking Barack's wife is born in the
model often fails to connect the dots.
Exactly, completely blanks.
Okay, let me play devil's advocate for a second. Why does this actually matter? If the model can get the right answer by just thinking out loud, I mean, if chain of thought gets us to 1964, why do we care if it can't do it instantly in its head? Why not just let it spit out the extra tokens?
That's a great question, and it comes down to the fundamental nature of how knowledge is represented in the network. If models cannot implicitly reason, they are forced to store knowledge redundantly.
Redundantly how?
They essentially become giant, bloated lookup tables rather than systems that learn the underlying compressed rules of reality. Think about the memory footprint. If a model has to separately memorize Barack's wife is Michelle, Michelle is born in 1964, and Barack's wife is born in 1964, that is highly inefficient.
It's essentially memorizing every possible path through a graph rather than just memorizing the nodes and learning how to traverse them.
Precisely. It's a scaling nightmare.
Yeah.
You need infinite parameters to store every possible combination of facts in the universe.
Right.
Furthermore, it makes updating facts nearly impossible. Let's say a new historical document proved Michelle was actually born in 1965.
Okay.
If you update that single atomic fact in a model lacking implicit reasoning, it wouldn't automatically update the downstream fact about Barack's wife. It fundamentally fails at what we call systematic generalization.
So you'd have to go in and surgically update every single combined fact that relied on her birth year.
Exactly. Which is an absolute nightmare for anyone trying to build a reliable enterprise knowledge base. It's the difference between knowing a bunch of disjointed trivia and actually understanding the topological structure of the world.
So to study this phenomenon deeply, you can't just use the open internet, right? It's too messy. You never know what GPT-4 has already seen in its training beta.
Exactly. The open internet is fundamentally contaminated. If a model successfully answers Brock's wife is born in 1964, you don't actually know if it implicitly reasoned that out or if it just read a Wikipedia article that explicitly contained the phrase Brock's wife was born in 1964.
Which ruins the experiment.
Right. To isolate the variable of pure reasoning, you have to operate in a vacuum. You have to create a synthetic world.
Walk us through what that synthetic world looks like. How do you build a vacuum to test AI logic?
You build a highly controlled knowledge graph. It consists entirely of entities, relations, and values. In the specific setup used to isolate this grokking phenomenon, a graph is created with thousands of abstract entities and hundreds of different relations.
Okay.
The foundational building blocks of this world are called atomic facts. These are the unquestionable axioms of this universe: a subject, a relation, and an object. Entity A is related to entity B.
So no messy human language, no colloquialisms, just pure structured data nodes.
Correct. And from those atomic facts, you define inferred facts. These are the theorems derived from applying specific latent rules to the atomic facts.
Give me an example of that.
For example, if the rule is transitivity, and you have the atomic facts A is larger than B and B is larger than C, the inferred fact is A is larger than C.
Okay, I'm tracking. But how do you prevent the model from just memorizing the inferred facts too?
This is where the experimental design gets incredibly rigorous. You take all the atomic facts and perform a critical split. In distribution, or ID, versus out of distribution, or ODE. You put, say, 95% of the atomic facts into the ID bucket, and the remaining 5% into the ODE bucket.
Let me guess, the OD bucket is the control group.
It is the ultimate lie detector test for true AI reasoning. During training, you show the model all 100% of the atomic facts. So it knows the basic axioms for everything.
Right.
But you only show it inferred facts that are deduced from the 95% ID bucket. It never, ever sees an inferred fact that uses an entity from the 5% O bucket.
That is brilliant, because if the model only solves the ID test cases later, meaning it successfully deduces new inferred facts that belong to the exact same distribution it saw during training, it might just be doing fancy pattern matching.
Yes, it might just be mimicking the shape of the data it was exposed to.
But if it can solve the ODE test cases, if it can suddenly deduce a complex inferred fact using those 5% of atomic facts it never saw in a combined format, then it has achieved true systematic generalization.
It proves unequivocally that the model hasn't just memorized patterns. It has actually learned the fundamental mathematical rule of composition, totally independent of the specific entities involved.
It's like teaching a model the rules of chess using only games played by grandmasters and then throwing it into a board state that has never occurred in human history. If it can still find the mate in 3, it understands the game.
Exactly.
If it blunders, it was just memorizing past games. And that crucial distinction sets the stage for what I think is the most mind-bending part of this entire deep dive: grokking.
Grokking is a fascinating phenomenon. It has almost a mystical reputation in deep learning circles right now.
For those who might not be deep in the weeds of ML optimization, grokking comes from Robert A. Heinlein's sci-fi novel Stranger in a Strange Land. It means to understand something so thoroughly that you merge with it. In neural networks, it describes something incredibly counterintuitive. It's what happens when you keep training a model long after it has perfectly memorized its training data.
To understand why it's so strange, look at the typical timeline of a model training run. In these controlled knowledge graph experiments, a standard transformer model perfectly fits the training data at around 14,000 optimization steps.
Okay.
At this point, the loss in the training set approaches 0. It achieves over 99% accuracy. It has perfectly memorized the answers you asked it to learn.
But there is a catch.
A massive catch. At this exact 14,000 step mark, if you test the model's ability to generalize to new, unseen, in-distribution data, its accuracy is a dismal 9.2%.
9.2%. That is essentially random noise, depending on the output space.
Exactly.
Now, if I'm a standard machine learning practitioner watching my TensorBoard and I see my training accuracy hit 99% while my validation accuracy is sitting at 9%, I am hitting the kill switch.
Oh, absolutely.
That is the textbook definition of catastrophic overfitting. Standard practice says you trigger early stopping to save compute costs. You pack up, assume the architecture or the data is flawed, and you try something else.
And for a long time, that is exactly what everyone did. But here is the magic of grokking. If you ignore every conventional ML instinct you have, And you just stubbornly keep training the model, doing absolutely nothing different, just showing it the exact same training data over and over again for 50 times longer than it took to reach that initial 99% accuracy, something unbelievable happens.
The generalization accuracy suddenly spikes.
Yes, out of nowhere, the generalization curve rockets vertically. It climbs from 9.2% to near 100%. The model suddenly grokks the underlying rules of the dataset.
It transitions from a state of pure rote memorization into a state of deep generalized reasoning.
It has a mathematical eureka moment, just by staring at the same data for millions of extra steps.
Yeah.
This completely upends a major debate that constantly rages on ML Twitter right now. The prevailing wisdom from the biggest labs for the last 3 years has been, just scale it up, throw more data at it.
Right, the data wall.
The assumption is that if a model isn't reasoning, it hasn't reached the critical data size. But this grokking phenomenon completely busts that myth.
It dismantles the critical data size theory entirely. It proves that reasoning isn't simply a function of absolute data volume. Instead, it isolates a crucial, entirely different variable, the density of logical connections within the data.
Specifically, the ratio of inferred facts to atomic facts in the training set.
Yes. The researchers who first isolated this refer to it as the phi ratio. Let's really dig into the geometry of this because it's vital for anyone curating data sets right now.
Absolutely.
Think of the phi ratio as a measure of how densely saturated your training data is with complex logic versus simple facts. If you fix the phi ratio at 9.0, meaning there are 9 complex inferred facts for every 1 simple atomic fact, and you scale the total volume of data, the results are shocking.
What happens?
You can increase the total number of entities in your knowledge graph from 2,000 to 5,000 all the way up to 10,000. You are massively increasing the absolute size of the data set. But the speed of generalization, the exact step count where that vertical grokking spike happens, does not change at all. The curves practically overlap.
Wait, really? So adding 8,000 more entities, which is exponentially more data, didn't make the model figure out the rules any faster?
Not even slightly. Scaling the absolute volume of data did nothing to accelerate the model's transition from memorization to true reasoning. It just made the training epoch take longer.
Wow.
However, when you keep the entity count small and constant at 2,000, and instead crank up that phi ratio, changing the distribution to include a higher density of inferred facts relative to atomic facts, say moving from a ratio of 3.6 up to 18.0, the model groks the logic drastically faster.
So a denser concentration of complex examples triggers the eureka moment sooner.
Yes, exactly. At a high phi ratio of 18.0, the generalization curve almost perfectly matches the training curve. Grokking happens almost instantly without the massive 50x delay.
That is a massive operational takeaway for the listeners. If you're building a domain-specific model, let's say a medical AI that needs to diagnose rare diseases based on overlapping symptoms, your instinct might be to just scrape every medical journal in existence and dump it into the pre-training mix.
Which is the standard approach right now.
Right. But this implies that strategy is fundamentally flawed. You don't need more journals, you need a highly curated data set where the density of complex diagnostic reasoning is artificially elevated. You need to saturate its diet with the rule being applied, not just expand its encyclopedia of raw facts.
It is a profound shift from focusing on data quantity to focusing on data topology. But of course, knowing that grokking happens based on data density isn't enough. As scientists and engineers, we need to know how.
Right. What is actually changing inside the neural network during those millions of extra steps?
Which leads us directly into the mechanistic interpretability side of things.
I love this field. Because it's one thing to look at a loss curve drop on a chart. It's another thing entirely to try and read the mind of a matrix. To an outsider, a transformer is just billions of floating point numbers multiplying together. It's a black box. How do we actually extract meaning from that?
We have to literally map the circuits of reasoning inside the model. And to do that, the interpretability community has developed some cutting-edge tools. 2 of the most powerful are the logit lens and causal tracing.
Let's break those down. What is the logit lens?
To understand the logit lens, you have to remember that a transformer processes text sequentially through its layers. It doesn't formulate the whole answer at once. It refines an internal representation called a hidden state as it moves from layer 0 up to, say, layer 8.
Right.
Normally, we only decode the very last layer to see the final word the model chose. The logit lens essentially takes the intermediate hidden states from the middle layers, say layer 3 or layer 5, and prematurely decodes them using the final vocabulary projection matrix.
It's like interrupting the model halfway through its thought process and demanding, what are you thinking about right now?
Precisely. It allows us to see what concepts or entities the model is focusing on before it finalizes an answer. If we ask about Brock's wife, the logic lens might show us that by layer 4, the model's internal state is heavily activating the word Michelle, even though it hasn't output anything yet.
It's like reading the rough drafts before it hands in the final essay. Okay, and what about causal tracing?
Causal tracing is even more interventionist. It's how we prove cause and effect rather than just correlation. First, you do a normal run of a prompt and record the activation values of every single neuron.
Makes sense.
Then you do a perturbed run. You tweak a specific input word, maybe changing Brock to Bill so that the final correct answer changes. You record all the neurons for that run too.
So you have 2 different maps of the brain under different conditions.
Right. And then comes the actual intervention. You run the original Brock prompt again, but midway through the computation, you manually overwrite the neuron activations in a specific layer with the activations you recorded from the Bill run.
Whoa.
Yeah. If forcibly injecting those specific neurons causes the model's final output to flip, you have just found the exact physical pathway, the causal circuit, responsible for passing that specific piece of information.
That is incredibly cool. You are essentially performing neurological surgery on the AI to see which wires do what. So armed with the logic lens and causal tracing, we can peek inside the transformer's brain after it is fully grokked.
Exactly.
And to test its reasoning, we evaluate 2 distinct types of logic tasks: composition and comparison. Let's define those clearly.
Composition is the sequential logic we discussed earlier. A points to B and B points to C. Brock's wife is Michelle. Michelle was born in 1964. Therefore, Brock's wife is born in 1964. You have to traverse the graph sequentially, one hop at a time.
And the other one?
Comparison, on the other hand, is evaluating 2 separate entities against each other. For example, given the atomic facts Donald Trump's age and Joe Biden's age, the prompt asks, which one is older?
This is where the interpretability analysis drops a revelation that I find completely mind-blowing. When you look at the fully grokked transformers, they successfully learn to generalize on in-distribution data for both composition and comparison. They hit near 100% accuracy.
Yes, on the in-distribution data.
BUT, when you hit them with the lie detector test, the out-of-distribution data using entities they've never seen in a complex prompt, they fail systematically on composition, 0% accuracy. Yet they succeed brilliantly on out-of-distribution data for comparison.
It is a shocking divergence. The obvious question is why? Why does the transformer completely fail at applying the sequential composition rule to novel data, but perfectly applies the parallel comparison rule to novel data?
Right.
To find out, we have to deconstruct the exact causal circuits the model formed during that extended grokking phase. Let's start with the circuit that fails, the composition circuit.
Walk us through the anatomy of that failure. If we're looking at a standard 8-layer transformer, what does the internal wiring look like when it tries to solve the Brock and Michelle prompt?
Causal tracing reveals a highly rigid sequential circuit. The model essentially splits the cognitive load across its depth. The lower layers, layers 0 through roughly layer 4 or 5, act as a retrieval engine for the first hop of the logic chain.
Okay, what are they retrieving?
They take the inputs, Brock and wife, query their internalized parametric memory, retrieve the atomic fact, and then they physically store the bridge entity, Michelle, in the hidden state vector at layer 5.
Hold on, let's visualize this. What does storing actually mean in this context? It's not a hard drive.
Right. It's not a database entry. It means the mathematical representation of the token Michelle is highly activated in the vector space of layer 5. The model is holding that concept in its active working memory at that specific depth.
Got it.
Then the upper layers, layers 5 through 8, take over. They take that bridge entity, Michelle, and process the second hop with the next relation in the prompt, born in to compute the final output, 1964.
So it's literally passing a baton. Lower layers do hop 1, get the answer, hand the baton to layer 5, and the upper layers take the baton and do hop 2. That sounds incredibly logical. Why does this exact mechanism cause a catastrophic failure for out-of-distribution data?
To understand the failure, you have to look at the architectural limitations of a vanilla transformer. A standard transformer is non-recurrent. It processes information strictly sequentially upwards, from layer 0 to layer 8.
Okay.
It does not share memory horizontally or backwards across its layers. The vector only moves up. It can never go back down to query the lower layers again.
So the flow of time is strictly one way.
Exactly. Now remember how the out-of-distribution data was structured in the training set? The model saw all the atomic facts, but it only ever saw them in isolation. It never saw an ode entity acting as a second hop in a complex logical chain. Because of this, the model never had any incentive during training to store those specific ode facts in the upper layer's parameter weights. The optimization process essentially localized all ode knowledge in the lower retrieval layers.
Oh, wow. I see the trap. It's a geographical issue inside the network. When the model tries to reason about an ode prompt, it actually executes the first hop perfectly. The lower layers know the fact, they do the math, and they successfully hand the baton to layer 5.
Yes. But then the upper layers take the baton, they look for the second connection, and they hit a brick wall. The necessary atomic fact for the second hop simply does not exist in the weights of layers 6, 7, or 8.
Because it was only ever stored in the bottom.
Right. The information is physically trapped in layers 0 through 4, but the architecture strictly forbids layer 7 from looking down at layer 3.
That is a staggering blind spot. The model mathematically knows the answer, but because of the one-way street of the transformer architecture, the active computational layer can't access the memory layer.
Which means standard transformers, by default, reduce compositional logic to linearized pattern matching. They don't learn a universal abstract rule of composition. They learn a highly rigid localized pathway that relies on specific facts having been preloaded into specific layers during training.
That makes total sense, but then it begs the opposite question. Why does the comparison task succeed? Let's deconstruct that circuit. If we're asking the model to compare the age of Trump versus the age of Biden, how is the architecture bypassing that geographical memory trap so that it works perfectly even for ode data?
Because the model learns a completely different parallel circuit for comparison. During grokking, it figures out that it doesn't need to pass a baton sequentially. Instead, the lower layers retrieve the age attributes for both entities simultaneously.
Interesting.
It pulls Trump's age and Biden's age from parametric memory and stores them side by side in the active hidden state at layer 5.
So there is no second hop. It fetches everything at once.
Exactly. Then, the upper layers don't need to fetch any new facts. They simply fetch a logical label, older, younger, or theory, based purely on a mathematical comparison of those two values that are already sitting in the active working memory.
And there's the breakthrough. Because the atomic facts, the ages, are being retrieved and stored in the exact same geographical region, the lower layers, for both in-distribution and outer-distribution data, the model can systematically generalize.
Yes.
The upper layers don't have to worry about whether a fash was memorized in layer 7 or layer 2. They are just executing an operator function on whatever the lower layers handed them.
It proves a profound capability of these models. Transformers can absolutely learn parallel solutions to seemingly sequential problems. When a problem can be solved by parallel retrieval, the transformer achieves true systematic generalization. But when a problem fundamentally forces sequential cross-layer retrieval, the non-recurrent architecture breaks down.
This highlights exactly why mechanistic interpretability is so crucial to the future of AI. If you just looked at a standard benchmark score, you would conclude, oh, the model is bad at reasoning. But when you dissect the brain, you realize, no, the model is excellent at reasoning, but its short-term memory architecture is physically isolating the data.
It changes the problem from an intelligence issue to a plumbing issue.
Exactly, a plumbing issue. Okay, so we've mapped the circuits, we know what the reasoning pathways look like, but that brings us to the most fundamental question of this entire deep dive, the physics of grokking.
Right.
Why does the model build these specific circuits? What actually triggers that eureka moment after 14,000 steps? Why does it suddenly abandon rote memorization and switch to efficient reasoning?
To understand the why, we have to look at the physics of the optimization process itself, specifically a concept called circuit efficiency. When a neural network is training, it's essentially exploring a massive high-dimensional landscape, looking for the easiest way to map inputs to correct outputs. Early in training, it almost always discovers the memorizing circuit first.
Because memorization is cheap and easy.
Very easy. The memorizing circuit essentially brute forces a direct, unique pathway from every specific question directly to its answer. It doesn't bother building a first hop and a second hop infrastructure. It just memorizes that prompt A equals answer B.
It's like a high school student cramming for a history exam. They don't understand the geopolitical causes of World War I. They just memorize the exact wording of 500 flashcards. It gets them an A on the test, but if you ask them a conceptual question, they blank.
That's a perfect analogy. But here is where the phi ratio, the density of complex facts, comes back into play. As the number of complex inferred facts increases, this memorizing circuit becomes incredibly bloated.
How bloated?
Storing a unique pathway for every possible combination of entities and relations requires a massive, tangled mess of parameters. It's highly inefficient. On the other hand, buried somewhere in that high-dimensional landscape, the model eventually stumbles upon the generalizing circuit.
The reasoning circuit, the one that uses the baton pass or the parallel fetch.
Yes. The generalizing circuit is initially much harder to find and learn. It requires setting up very distinct structural retrieval mechanisms. But once it is formed, it is vastly more efficient. It requires exponentially fewer parameters to maintain because it reuses a small set of atomic facts to answer endless combinations of questions.
Okay, I follow that. The reasoning circuit is leaner and more efficient. But if the model has already hit 99% accuracy using the bloated memorization circuit at step 14,000, why would it ever switch? It's already getting an A on the test. What pushes it to abandon the easy path and snap into the hard, efficient path?
It is the relentless physical pressure of the optimization algorithm itself. Specifically, the combination of the optimizer they use, typically Atom W, and a crucial explicit regularization technique called weight decay.
Let's really dig into weight decay because it's one of those terms that gets thrown around in ML tutorials, but its physical impact on the network is rarely visualized. What is it actually doing to the matrix numbers?
Think of weight decay as a constant artificial gravitational pull on every single parameter in the model. At every single step of training, the optimizer adds a small mathematical penalty proportional to the size of the weights. It is constantly trying to pull every floating point number in the network back to zero.
It punishes complexity. It punishes large numbers. It's an algorithmic manifestation of Occam's razor.
Exactly. If a parameter isn't actively contributing to getting the right answer, the weight decay will slowly erode it down to nothing. Now apply this to our two circuits. The bloated memorizing circuit relies on thousands of large, chaotic parameters to maintain all those unique flashcard pathways.
Right.
It is highly susceptible to the gravitational pull of weight decay. The network is constantly fighting to keep those numbers high, which requires massive energy.
And the generalizing circuit is lean. It relies on a few strong, highly structured pathways.
Yes. Over an extended training time, those millions of extra steps during the grokking phase, this constant grinding pressure makes the bloated memorization circuit fundamentally unsustainable. The physics of the optimization literally squeeze the bloat out of the network.
So it forces a change.
To survive the weight decay penalty while simultaneously maintaining that 100% accuracy on the loss function, the model is physically forced to abandon the memorizing circuit and snap into the highly efficient generalizing circuit.
That is beautiful. It is literal algorithmic evolution. Survival of the fittest, where fitness is defined by mathematical efficiency. The environment, the optimizer, becomes so hostile to bloat that only pure logic can survive.
And the researchers actually proved this dynamically, didn't they?
They did. They ran an experiment to test this exact theory. They took the same setup, but they manually turned up the weight decay factor. They increased the gravitational pull, punishing the bloat.
And what happened? The model grokked drastically faster. The vertical spike in generalization happened tens of thousands of steps earlier. By increasing the penalty for inefficiency, they forced the model to abandon memorization and discover reasoning much sooner.
That's amazing.
It confirms the theory perfectly. Grokking isn't some mystical property of neural networks. It is the directly observable phase transition of a network being compressed into efficiency by optimization pressure.
That is just incredible. It demystifies the entire process. Okay, we've established the deep theory, the mechanistic interpretability, and the physics of the training phase. Now, it is time for the ultimate showdown. How does a model that has undergone this intense, grokking-induced phase transition stack up against the absolute titans of the industry? Let's talk about the real-world performance benchmarks, the David versus Goliath scenario.
To really test the limits of implicit reasoning, standard benchmarks aren't enough. You have to design a task that pushes models to the absolute edge of their capabilities. The researchers designed what they call the complex reasoning task.
Walk us through the setup of this gauntlet.
They created a massive tangled search space utilizing complex rules of transitivity and symmetry. They generated a highly dense database of over 28,000 interlocking facts. To successfully answer a single query in this benchmark, a model has to sift through those 28,000 facts, find a highly specific hidden bridge entity out of thousands of potential distractors, and then apply multiple logic rules backwards and forwards across the graph.
And crucially, there are no surface-level linguistic clues to guide the search, right? The entities are abstract. It's pure, raw, topological logic. It's like finding a needle in a haystack where the needle is a multi-step algebraic equation.
Precisely. So they put the current state-of-the-art giants to the test. Models like GPT-4 Turbo and Gemini 1.5 Pro. Now, these massive foundational models approach a task like this using non-parametric memory.
Meaning they aren't trained on the 28,000 facts. The facts aren't baked into their weights.
Right. Instead, you rely on their massive context windows. You literally just shove the entire database of 28,000 facts into the prompts and say, read all this, hold it in your working memory, and answer the complex query.
Okay.
They even gave the models a massive advantage by using retrieval augmented generation, or RA. They used algorithms to prefetch the most relevant facts, the exact two-hop neighborhood of the target entities, and fed those directly into the prompt to help the giants out.
The ultimate open book test with a study guide. So how did the trillion parameter giants do?
The failures were staggering. Even with RREG feeding them the most relevant facts, GPT-4 Turbo scored just 33.3% accuracy. It's basically guessing wildly. Gemini 1.5 Pro scored slightly better at 37.3%. Despite their massive compute power and huge context windows, they were completely overwhelmed by the topological complexity of the search space.
33%. That is shocking for a model as capable as GPT-4. But let me stop you right there, because earlier we talked about chain of thought prompting. The whiteboard explicit reasoning. Doesn't forcing the model to think out loud, step by step, fix this exact kind of problem? That is the standard industry workaround for logic puzzles.
And this reveals a crucially important, highly counterintuitive reality about massive context windows. For a search space this large and unstructured, chain of thought actually made the models worse.
Wait, thinking out loud made them dumber?
Significantly. When prompted to use chain of thought, Gemini's accuracy plummeted from 37% down to an abysmal 12%.
12%. It actively degraded its own performance by trying to reason explicitly. Why? How does that happen?
Because when a model is forced to verbalize a search across a massive, highly dense logic tree, it gets confused by its own output. It loses its place in the context window. It starts hallucinating fake facts to bridge logical gaps it can't figure out. Or, in a huge percentage of the failure cases, the model simply gave up. It would output a long chain of reasoning and then conclude that the answer was mathematically impossible to decide, even though the necessary facts were sitting right there in its prompt.
That perfectly illustrates the limit of non-parametric memory. Having text in your prompt is not the same as understanding the structure of reality. Reading a list of coordinates does not give you a map.
Right.
So enter the David in our story. The researchers took a tiny standard transformer model, but instead of an open book test, they trained it on the facts using the exact hi-fi ratio and extended grokking protocols we just discussed. They forced the knowledge purely into its parametric memory. No RAG, no context window cheating. It had to answer purely from its internalized weights. What was the score?
The fully grokked, parametrically trained transformer achieved an astonishing 99.3% accuracy.
99.3% versus GPT-4's 33.3%. Utterly destroyed. It wasn't even close. How is that mechanically possible? How does a tiny model beat the trillion parameter giant at its own game?
Because parametric memory, when it has been fully grokked, unlocks a unique superpower that RA and in-context learning fundamentally lack. It achieves what is called deep compression and integration. During that massive extended grokking phase under the pressure of weight decay, the model literally restructures its own brain to map the exact logical topology of the dataset.
It doesn't just store the facts, it stores the shape of how those facts connect to each other.
Exactly. This deep structural integration allows the model to instantly traverse incredibly complex logic trees entirely internally. It intuitively sees the connections. RE and massive context windows simply cannot navigate that topology because they are just reading flat text on a page. They have the data, but they lack the integrated structural logic.
It's the difference between handing someone a massive Excel spreadsheet of 28,000 flight coordinates versus handing someone a fully rendered 3D interactive globe. The grokked model has the globe burned into its visual cortex. It just looks and knows.
That's a great analogy.
Which brings us to the crucial takeaway. Implications for practitioners and the future of AI architecture. If you are listening to this and you build AI systems, What is the actionable insight here? Because to me, the loudest message is RAG is not a silver bullet.
It absolutely isn't.
Yeah.
We are currently seeing a massive industry trend of companies throwing millions of dollars at developing infinite context windows, million token, 2 million token contexts. But this research proves that shoving 10 million tokens into a prompt does not equal reasoning.
Right.
If your task requires deep, multi-hop logic, the foundational model will just get lost in the noise of its own context window.
So if I'm building a specialized enterprise model, say an AI for a law firm that needs to link highly complex legal precedents across thousands of case files, or a system for complex software debugging, I cannot rely purely on prompt engineering or a vector database. I have to leverage parametric memory. I have to train the model.
And you have to train it correctly.
Yeah.
You must engineer the distribution of your fine-tuning data. You have to ensure a high-phi ratio, a high density of inferred complex reasoning paths relative to basic facts in your training set.
Okay.
You have to mathematically force the model to see the rules applied over and over again. And crucially, you have to abandon standard early stopping metrics. You have to be willing to endure the compute cost to push the model through that phase transition into true grokking.
But we also have to talk about fixing the transformer architecture itself. Because we can't ignore the massive vulnerability we mapped out earlier, the composition out of distribution failure, the fact that standard transformers geographically trap information in lower layers is a fundamental limitation of the non-recurrent design. We have to fix the plumbing.
And that is the next frontier of model architecture. The solutions point strongly toward introducing cross-layer memory sharing. We have to break the rigid, one-way sequential barrier between the lower retrieval layers and the upper computation layers.
What does that look like in practice?
The researchers ran preliminary experiments utilizing concepts from universal transformers, which utilize parameter sharing schemes. Essentially, the weights of the lower layers are mathematically tied to the upper layers, forcing a shared representation space.
Fascinating.
They also discuss explicit memory augmentation, building a persistent internal scratchpad, a dedicated memory vector that any layer can read from or write to at any time, regardless of depth.
A unified working memory.
Exactly. And when they implemented these types of parameter sharing schemes in their experiments, it successfully bridged the gap. The model was finally able to unlock true out-of-distribution composition because the upper layers could finally see what the lower layers had retrieved.
So the future of AI isn't just scaling up vanilla one-way transformers until we run out of GPUs. It is fundamentally altering their anatomy to allow cross-layer memory and recurrent thought. That is an incredibly exciting horizon. All right, we've covered the complex math, the internal mechanics, and the benchmark obliterations. It is time for my absolute favorite segment to close out the deep dive. It's time for Novel Notions.
I'm ready. Let's hear what you got this time.
For those new to Talk Tensors, Novel Notions is where we take the trajectory of the tech we just discussed and pitch some totally outlandish yet mathematically plausible new ideas. Quick disclaimer, this segment is for entertainment purposes only. Do not go base your startup's entire Series A funding on what I'm about to say.
I will personally hold you to that disclaimer. What is Novel Notion number 1?
I call it the grokking phase shift protocol. Think about how massive foundational models are pre-trained right now. Companies spend hundreds of millions of dollars to train models like Llama or GPT for roughly 1 or 2 epochs over a massive, chaotic scrape of the entire internet. The singular goal is to memorize human knowledge as fast as possible. But what if we radically alter the endgame of that pre-training run?
Altered it how? What's the mechanism?
We introduce a phase shift protocol at the very tail end of the massive internet training run. We stop feeding the model messy, unverified internet data. We sever the cord entirely. Instead, we lock the model in what I call a simulated logic gym. We swap out the internet for a hyperdense, perfectly clean data set of synthetic axioms, mathematical theorems, and pure logical deduction. We engineer the phi ratio of this data set to be astronomically high, maybe 50-to-1 complex logic to simple facts.
Okay, I see where you're going.
We crank up the optimizer's weight decay to create massive gravitational pressure on the parameters, and we let the model train for billions of steps on this tiny, closed synthetic data set.
So you are inducing a forced extreme grokking phase on a massive, already pre-trained model. What is your expected impact here?
The impact is that the optimization pressure forces the massive model to structurally collapse its bloated, chaotic internet memorization circuits into universally efficient reasoning circuits. The model's brain fundamentally crystallizes under the pressure. The resulting foundational model wouldn't just be an encyclopedia of facts, it would have an intrinsic, unbreakable logic engine burned permanently into its deepest weights. Because the circuits are optimized for absolute universal efficiency, it would theoretically eliminate hallucinations entirely. It literally wouldn't have the bloat required to hallucinate.
I genuinely like the theory behind that. It is an extreme form of alignment through physics, rather than trying to use RLHF, reinforcement learning from human feedback, which is just putting behavioral band-aids over a chaotic system. If the circuit efficiency theory holds true, forcing a massive weight decay phase on a highly dense logic dataset could act as a universal structural compiler for the model's chaotic internet knowledge. What is your second novel notion?
Novel notion 2 is aimed directly at solving that architectural plumbing issue, the out-of-distribution composition failure. I call it the parametric RAG Ouroboros architecture.
Ouroboros, the mythical snake eating its own tail. Very fitting for a recurrent architecture. How does it work?
Exactly. Instead of using external RAG to fetch text documents from a slow vector database, we physically alter the transformer to create an internal, infinite scratchpad. We take the bottom 4 layers, layers 0 through 3, and we entirely decouple them from the computation engine. We train them to act purely as an internal, highly compressed parametric database of atomic facts. They become the model's subconscious.
Okay, a localized memory bank.
Then we build the recurrence loop. As the model encounters a highly complex prompt, it doesn't just process sequentially from layers 0 to 8 and output a blind guess, it loops. The top computation layer, layer 8, mathematically queries layer 0 repeatedly. It extracts atomic facts one logical hop at a time, entirely within its own parametric weights, looping the hitting states back to the bottom until the logic chain fully resolves.
What's fascinating about that architecture is that you are essentially taking the massive success of the comparison parallel circuit, where everything is efficiently stored and retrieved from the lower layers, and you are combining it with a recurrent control mechanism.
Precisely. And the impact. You create a model that can perform infinite hop reasoning on novel data without ever needing an external database, a search engine, or an internet connection. It effectively becomes a completely self-contained reasoning engine. It could theoretically be capable of autonomous scientific discovery because it can traverse its own massive, compressed parametric knowledge graph infinitely, checking its own logic in a closed loop before it ever outputs a single token to the user.
A self-contained reasoning engine that doesn't rely on brittle external retrieval pipelines. That really is the holy grail of artificial general intelligence. It relies entirely on solving the cross-layer memory sharing bottleneck. But the grokking research proves that the parametric memory is absolutely capable of holding the required topological structure if we just give it the right architecture and the right optimization pressure.
And that is exactly why this research is such a fundamental paradigm shift. We have to stop just throwing blind compute and unstructured data at the wall, and we need to start engineering the fundamental physics of the model's reasoning circuits.
It's an exciting time to be building in this space.
It really is. Thank you to everyone for joining us on this deep dive into the mechanics of grokking and implicit reasoning. But before we sign off, I want to leave you with one final, slightly provocative thought to mull over on your own. We've spent this entire time talking about artificial neural networks needing massively extended exposure to the same data under intense physical optimization pressure just to undergo a phase transition from rote memorization into true intuitive reasoning. But think about the human brain. Think about how a human expert, a chess grandmaster, a master mechanic, a seasoned doctor develops what we call intuition. They don't gain intuition the first time they read the textbook. They gain it after thousands of hours of looking at the exact same types of problems over and over while their biological brain constantly tries to optimize its energy consumption. What if human intuition, that gut feeling of instant logic, is literally just our own biological neural networks undergoing a grokking phase shift after decades of life experience? What if the universe itself simply optimizes for circuit efficiency? Keep questioning the context, keep pushing the boundaries, and we'll see you on the next deep dive on Talk Tensors.